Welcome to Brain Vision.
So in this problem, we're going to be taking a tube, and on one end, it's connecting into a vein. And on the other end, it's going to connect to a reservoir. This is going to be open to the air, has some fluid in it, and we're given the density. Okay. The height of the reservoir above the vein is going to be denoted by H. And we're given a gauge pressure of the vein. So I'm going to write that as PG. We'll talk a bit about what that means. So first, what are we trying to find in this problem? Well, we're looking for the minimum height so that water will flow from the reservoir into the vein. And so just to make sense of all the values we're given, let's talk about what a gauge pressure is. So a gauge pressure is not an absolute or total pressure. So here, we're not talking about the total pressure in the vein. We're talking about the relative pressure inside the vein to outside the vein. So inside the vein, right here, outside the vein, that's going to be at our reservoir. So it's going to be really important to keep that in mind as we make sense of things. And so let's really quickly just go over the conditions that we have. So notice that the density is constant. And we're also told in the problem that we don't have to deal with any viscosity effects. We can ignore that. And so when we're first considering the problem, nothing in the fluid is moving at first. So it's a static fluid scenario. So nothing too complicated is going on here. Ultimately, we're going to need to relate the pressure differences in the fluid to the height differences. And so sort of using that as intuition, equation 12.6 from the text is going to be pretty handy. So I'm just going to go ahead and write that down. And then we'll make sense of the terms. Okay, so sorry if this is a bit hard to read, but this is P, and that's going to be the pressure at any given depth. And so here, with depth, we want to think about, height below the reservoir. P naught is the pressure at the surface. So again, that's the surface of the fluid, which is the reservoir. Rho. Oh, sorry. So this is supposed to be a plus. Okay, looking much better. So anyway, moving on. Rho is the density, which we're given. G is the acceleration due to gravity. Just go ahead and write that value down. And H is our height. And so we're looking to solve for height. So let's go ahead and just rearrange this equation to get it in terms of H. So if we subtract P naught from both sides first. Divide out the rho G on both sides. Okay, so now we have this equation rearranged in terms of the height, which is what we're solving for. And let's just really quickly take a look at the equation and see what we have and what we don't have. So we're looking to solve for H. We are given the density, so we have that. We know the acceleration due to gravity. And here we have P minus P naught. That's a pressure difference or a relative pressure. And so keep in mind what we're given in the problem is a relative pressure. So let's just really quickly make sure it makes sense. So if H is the height of the reservoir above the vein, Then P here is going to be the pressure at the depth of the vein. And P naught is going to be the surface pressure. So it's going to be at the reservoir. So looking into these terms, this is actually the gauge pressure. So what we're saying is, another way to write this in terms of our variables that we have is P minus P naught. So we have everything we need. So let's go ahead and plug these values in and solve for H. Throwing gravity in. Okay, and so if you evaluate this in your calculator, you should get approximately 0.58, and we're talking about height, so it's going to be units of meters. And so that's the minimum height where you'll start to see fluid flowing from the reservoir into the vein.